Hey, what's up, Precalculus students? Today we're looking at 4-2 real zeros. So before we begin talking about real zeros, let's talk about the remainder theorem, because that's important in helping us determine the real zeros. So the remainder theorem says if f of x is divided by x minus c, the remainder is f of c. So it's kind of wordy, and like a lot of mathematical statements such as this, it's kind of hard to decipher. So if we're looking at a function, right, f of x, and we divide it by something else, x minus c, then the remainder is f of c. So what they're saying is that if I plug in the c there into the function, then I should get the same thing as if I did the long division and found the remainder. All right, so let's see how this applies. So find the remainder if f of x equals x cubed minus 4x squared minus 5 is divided by, okay, so first we're looking at x minus 3. So be very careful here. Notice the form is x minus c, right? So one way to think about it is we're just taking the minus and taking the number next to it. So we're plugging 3 into our function. Now the other way to think about it is we're looking at the 0, right? So what makes this 0? That's 3. So what we're going to do is we're going to do f of 3, meaning we're going to plug our 3 into all of our x's in our function. So we have 3 cubed minus 4 times 3 squared minus 5. All right, so let's go ahead and simplify this. 3 cubed is 27. 3 squared is 9 times 4 is negative 36. And then minus 5. So 27 minus 36, negative 9, minus 5 is negative 14. So this would be the remainder of our function, okay, from the remainder theorem. Okay, so for this one, we're looking for zeros again, right? Or we'd have to look at it at the plus being actually minus negative, which is complex. So let's just look at the 0 here. So what plus 2 is 0? Negative 2. So we're doing the f of negative 2. We're substituting 2 in for all our x's. Negative 2. Okay? And we're simplifying. So negative 2 cubed is negative 8. Be careful with your signs. Negative 2 squared is 4 times negative 4 is negative 16. So negative 8 minus 16, negative 24. Negative 24 minus 5 is negative 29. So this would be our remainder. Now let's look at why the remainder is important, right? Because otherwise, why would we be doing it? All right, so we use the remainder theorem in order to find factors. Right, so if our remainder is 0, then it's a factor. All right, so we're going to do the same thing we did last time. But this time we're looking for specifically if the remainder is 0. So I'm going to do, for this one, the 0 is 1, right? 1 minus 1 is 0. So I'm doing the f of 1. So 2 times 1 cubed minus 1 squared plus 2 times 1 minus 3. So then 2 times 1 cubed is 1. So 2 times 1 is 2. Minus 1 squared is 1. Plus 2 times 1 is 2. Minus 3. So 2 minus 1 is 1. 1 plus 2 is 3. 3 minus 3 is 0. So what we know, because our remainder is 0, is yes, this is a factor. Yes, x minus 1 is a factor. Okay, let's do the same thing for the second one. We're finding the 0 here, so what plus 2 is 0? That's negative 2. Let's change colors. So we're doing f of negative 2. So 2 times negative 2 cubed minus negative 2 squared plus 2 times negative 2 minus 3. Okay, so first term, negative 2 cubed is negative 8 times 2 is negative 16 minus negative 2 squared is positive 4, and then plus 2 times negative 2, which is negative 4, and then minus 3. So this one's not going to come out, right? Negative 16 minus 4 is negative 20, minus 4 is negative 24, minus 3 is negative 27. So no, x plus 2 is not a factor. Okay, so we're building this idea using the factor theorem because we're going to eventually get to finding all the zeros of a polynomial function. But for now, we're just practicing the tools that we need in order to get there. So the remainder theorem is an important one in eventually talking about finding all the zeros of a function and those that are not given to us, right? These are given to us. It's easy for us to check the ones that are given to us. We're going to try to build up to the point where we can just find all the zeros for any polynomial function. All right, so another step in finding all the zeros in a polynomial function, we wouldn't want to have to test infinitely many numbers, right? That would be ridiculous, and it would take us forever, infinitely long maybe. So the cool thing is that a function can have as many zeros as its degree. So if we have like 2x cubed, right, as our leading term, the most zeros we can have is the same as the degree. So this at most can have 3 zeros, is what it's saying. Okay, and of those, the potential zeros we can find by taking all of the combinations of factors of the last term divided by the first term. Okay, so if we look at this next example, it says list the potential zeros of f of x if f of x equals 2x cubed plus 11x squared minus 7x minus 6. Okay, so look at the last term. The last term is 6, right? So we can have positive and negative. We're going to list all the factors of 6. So 1, 2, 3, and 6. Right, there's no other factors of 6. There's no other things we can multiply to get 6. 1 times 6 is 6. 2 times 3 is 6. And then the first one is 2. So that's pretty easy. 2 is 1 and 2. Notice I'm putting all the positive and negatives because we don't know exactly the signs there. Now that we listed it, so right, the first step was, okay, we're going to list all the possible factors. So step 1, list factors. Okay, and then we're going to do all the combinations here. So step 2, we're going to do all the combinations. So let's start, notice it's the last term over the first term. So we could have positive and negative 1 divided by 1, which is 1. Positive and negative 1 divided by 2. So that would be a half. Okay, so we're just going to go, we're going to go 1 by 1 for the last, divided by both things for the first. So then we have 2 now divided by 1, which is 2. And then we have 2 divided by 2, which is 1. But we already have 1 listed, so we don't have to list it again. Right? We don't want to be redundant with that. Okay, now that we finished the 2 here, let's move on to 3. So 3 divided by 1 is 3. 3 divided by 2 is 3 halves. Okay, now we're done with 3. Let's move on to 6. 6 divided by 1 is 6. And then 6 divided by 2 is 3, but we already have 3 listed, so we're not going to list it again. So these are all the possible zeros that we could have. Positive and negative 1, positive and negative 1 half, positive negative 2, positive negative 3, positive negative 3 halves, positive and negative 6. So this is 1, 2, 3, 4, 5, 6, and then the positive and negatives for each of them. So there's 12 different, you don't have to write this down, but there's 12 different possible zeros. Right? Some might have less, some might have more, but in this case we have 12 different ones. So the positive and negative counts as 2 different ones, each of them. Okay, so that's it. It's a lot, a little bit. Well, it's kind of a lot, but it's